Good afternoon. We're going to start in section 10-4, and we'll start with something from our long past. Do we remember when we had ice boxes, not refrigerators? You do? Okay. Do you remember who delivered the ice?
The Iceman.
The Iceman. You know, remember his first name?
Bill Charles. Bill.
Yeah. It was Eli.
Vanilla.
So Eli, the Iceman, delivered the ice. Okay, and because we remember that from our childhood very vividly, we remember that in an inductive circuit, the voltage leads the current. So voltage.
I was going to say, where's the second one?
So voltage leads current. And in a capacitive system, which we haven't discussed yet because we don't know what capacitors are, the current leads the voltage. So if you ever forget those things, that's how you're going to remember it, because Eli the Iceman delivered ice to your house, and that's how you remember that. Which part don't you understand? That was before the Frigidaire.
Inductance.
Yeah. Inductance.
Inductance.
So your inductance is an L, which is chapter 10. Your capacitance is a C, which it won't be until probably chapter 11 or 12. Maybe before then.
Capacitance.
Capacitance. Farads. Henrys. L's are in Henrys. Go back.
Current leads voltage.
So on page 301, we have an XY plane, and we show voltage doing something, and we show current being 90 degrees out of phase. So this is my time axis, this is my amplitude axis. And so at time 0, voltage passes through 0, the current, so voltage, that guy, current, that guy. The current doesn't start going past 0 and starts going up until I'm 90 degrees out of phase with the voltage. So voltage happens before current in an inductive circuit. So the circuit they're showing is some AC power going through an inductor.
Before current.
Voltage across the inductor.
Voltage before current in an inductor.
Right. In an inductive circuit. Okay. Now, this is what we've been waiting for, I just know. X of L, which is our inductive reactance, is going to be 2 pi F for frequency, L for the inductance in Henry.
Reactance?
Yeah, inductive reactance. And we're going to measure this guy, and we're going to measure him in ohms. Okay, so I've got a 60 hertz signal, and I've got an inductor there, and it's 10 millihenry, and I have some inductive reactance. My inductive reactance is 2 pi frequency L, 2 pi 60 times 10 millihenry. Take my calculator. 2 times pi, 2 times pi times 60 times 0.01, and I come up with 3.77 ohms. Okay, so if this guy is 120 volts, if that's the case, then the current through the system would be that 120 volts, which would be an RMS value, divided by 3.77 ohms. So that's going to be 31.8 amps are flowing in that circuit. Now, if I look at something that's this is my real axis, this is my imaginary axis. My imaginary axis is the square root of -1. Then my resistance is on the real axis. My inductive reactance, X of L, is on the imaginary axis. And so this guy's going to be angle minus 90 degrees. When I divide that out, I'm going to get an angle of 90 degrees. So if the voltage has an angle of 0 degrees, which it did in my last example, the current is 90 degrees out of phase. It's not going to start going up until I get to 90 degrees, which is what happened in my last example. Okay, well, that was cool. If I have a squared times a cubed, what do I have? A to the 5th, right? If I have a cubed divided by a squared, what do I have? A. Okay, so what happens is if I have some voltage that's 120 degrees, angle 0, I can think of that as 120 degrees e to the j 0, where e to the j is that's some exponent, and if I have some x of L that is 3.77 ohms, and I say that's 3.77 angle minus 90, then that's the same thing as saying 3.77 e to the j. Now I'm going to have to put this in radians. So that would be minus pi over 2. But now if I took my voltage and I divide it by x of L, what I would be doing is taking my magnitudes and dividing them, and then I would be taking my angles and adding them. Because I have this guy on the bottom, so I got an angle of 0 minus a minus 90 to give me 90 degrees. So I end up with 90 degrees up there. So when I have I got a vector here A, and I got a vector here B, and I'm going to add A plus B. So I can go A, and then I can go B, and then I can have some resultant R. So A plus B is equal to R. And I can do that, A, B, R. I can also say that A has an X component and A has a Y component, and that B has an X component and B has a Y component. I can add those up and I can get the resultant in the X direction, the resultant in the Y direction. I can do that. And that's also allowed. So if I have imaginary numbers, which I'm going to have for the rest of the semester, and I want to add them or I want to subtract them, I want to be in rectangular form. So I can add the x components and add the y components. But if I want to multiply or divide them, I'm going to want to be in polar form. So that would be A angle theta, B angle phi. So if I wanted to multiply A times B, then that'd be A times B angle phi plus theta. If I wanted to divide A divided by B, I would have A over B angle phi minus theta. Because what's on the other side of the angle thing acts as an exponent. All right, so we're all happy with that? Now, if I have I have something 5 volts, 5 volts angle 37.5, and I want to change that to rectangular form, I could go and I could say, we'll let that be A, that the x component of A would be 5 cosine 37.5, and the y component of A is 5 sine 37.5. I could do that. Or I could take my calculator and put in 5, use the XY key, put in a 37.5, hit the equals key, and then I could go second function, change from polar to rectangular. Change from polar to rectangular. Okay, so I could go on my calculator and go 5, right there's the XY key, 37.5 equals second function, change to rectangular. Yeah, something messed up. 5 XY key, 37.5. Second function, change to rectangular. Notice that I have a little X up there. Oops, no, you don't notice, do you? So you notice that I have a little X up there in the corner that says that's my X component. So my X component is 3.97. So that's A in the X direction. And then A in the Y direction, I'm going to hit the XY key, and it's going to tell me my Y component is 3.04. 3.04. So now I have 3.97 plus 3.04 I, or we could be using a J, is what my A is. So if I had something, some vector 5 angle 37.5, and I wanted to add it to somebody, well, I can't add it because it's in polar form. I'm going to change it to rectangular form, 3.97 plus 3.4 I.
Can you write this?
Huh? Oh, you want me to move over to the other one?
Would be nice.
Well, normally you guys complain before I'm halfway through the lecture, switching back and forth. All right, now how many times am I going to have to do that before we get it through?
18. At least.
At least, yeah. So many, many times. So obviously we're going to do this over and over again until we get it right. Now there is some trig going on there that we're going to talk about later, but that's okay. We don't have to talk about it now. Okay. Now back to X of L, my inductive reactance is 2 pi FL. Now, if we remember, our angular velocity omega is 2 pi F. So we could write this as omega L if we wanted to. That's a lowercase omega. Doesn't look, it looks sort of like a W, but it's really
Is that an
supposed to
omega
be.
sign?
Yeah, that's an omega sign. Now, if I have a circuit, so I have some voltage here, and I have some inductors, and I know X of L1, X of L2, then X sub L total, the total inductive reactance is going to be XL1 plus XL2. This acts just like resistances does. It's going to be, it's in series, it's going to add. If I have something that looks like that, and I'm in parallel, XL1, XL2, then my total inductance 1 over 1 over XL1 plus 1 over XL2. Okay, now I guess that's enough. We can make it more complicated than that, but we're not going to.
No.
All right. Well, it'll be more complicated than that in a couple chapters anyway, so we'll let that be okay. So now I'm in section 10.5, and I'm dealing with a transformer. So what I'm going to do is I'm going to take a piece of steel, and I'm going to wrap some coils around it. I'm going to wrap some wire around it. I'm going to call this the primary side. Primary. And then I'm going to wrap some wire around it on the other side. I'm going to call this the secondary side. So what's going to happen when I put voltage, I got some AC voltage going in on this side of the. Now, if I had, let's take an inductor for a moment. This is an aside thing. So I got this inductor, and I'm going to hook it up to DC. What is it going to see? What is the frequency of DC? 0. So that's my frequency. So X of L is 2 pi FL. F is 0. So my inductive reactance is 0. As far in a DC circuit, that inductor, all it looks like is just a piece of wire. That's all it is. So it would be a short. So an inductive circuit, an inductive piece of equipment in a DC circuit would be a short. That could be a problem if I was drawing too much current. Okay, so if I take this transformer and I hook it up to some DC thing, all I'm going to end up doing is burning out my power supply. It's a short. But because it's AC going up and down, I'm causing 60 times a second, I'm causing a magnetic field to go back and forth. And because the permeability of the magnetic field in the metal is so much larger than air, on the order of several thousand times larger, I end up transferring this magnetic field over the other set of coils, causing voltage to be on the other side. So a transformer has a turn ratio. There's no N in ratio. I just know there isn't. All right, so turns primary to turns secondary. It might be 1 to 2, for example. Turns primary to turns secondary. The turns primary to turns secondary is going to equal to the voltage primary to voltage secondary. So if I have more turns on the primary, my voltage on the primary is going to be more. If I have more turns on the secondary, my voltage on the secondary is going to be more. So I could have a step-down transformer. I could be going from 4,000 volts to 120 volts. I would do that by a turn ratio. Normal transformers are greater than 95% efficient. So we normally just say, well, that's close enough to 100 and not worry about it. So the power on the primary side is going to equal the power on the secondary side. All right, so if V is still equal to IR, right? So as the, well, we don't want that. It is still equal to IR, but that's beside the point. Power is voltage times current. So if when the power goes, the power is going to remain constant. If the power remains constant, but the voltage went up, that means the current had to go down. So turns primary to turns secondary is equal to voltage primary to voltage secondary is equal to current secondary to current primary. So if I increase the voltage on the secondary, the amount of current I have necessarily has to go back down. If a transformer that's transforms the voltage downward would give me more current, potentially. Okay, so we're going to write that over again. Current turns primary to turns secondary is equal to voltage primary, voltage secondary is equal to current secondary, current primary. Now there's an impedance thing going on as well, and impedance is a word we haven't used yet, right? Say, so when we were talking about DC things, it had resistance. When we talk about AC things, they have impedance. So in the AC circuit world, we don't talk about resistance anymore, we talk about impedance. But it's the same thing, it's measured in ohms. So the square root of the impedance primary to the square root of the impedance secondary. Okay, so that's all happiness, right? I could have on the bottom of 305, I could have a circuit that is an air core transformer, so there's nothing there at all. I could have iron in there, or I could have some ferrite core, or I could have some exotic material in there. Whatever it is it is what it is. In the middle of 305, I see that I could use the same core to have a primary and secondary hooked up to, or I could do it, so I have a radio frequency transformer and I have an audio frequency transformer, depending on how I make it. The big transformers that are used on the power grid are huge things with great big fans on them. Why are they great big fans? Yeah, because although my efficiency might be approaching 100%, if I'm sending megawatts of power through that guy and he's 99% efficient, that means 1% of the power got dissipated into heat in the transformer. I'm going to have to get rid of it. So that's what that means. I can have a transformer. I have a dot thing here. So if I put a dot on this side and a dot up there, that's telling me how the transformer is wound. And so if my voltage is coming in like this, my voltage is going out and it's in phase because of the way the transformer is wound. If I go and I have a transformer that's, I got a dot there and I got a dot down here, that means that this guy's wound opposite of the other guy. So one guy's wound clockwise, the other guy's wound counterclockwise. When I look at the voltage, this guy's doing like that. This guy's going to be 180 out. It's going to be like that.
So you said the dot is the ground or what?
No, it tells me which way the transformer is wound.
Okay.
Because if when I put my finger, when I put my finger in the direction of the current, my thumb in the direction of current, and wrap it around the wire to find out which way the magnetic field is being formed. If I'm wound this way, the magnetic field's going that way. If I'm wound the other way, the magnetic field's going the other way. Okay. Now I can use these transformers in control circuitry, so our nuclear power plants were originally designed with control power transformers that did things like tell you what the temperature of the plant was, among other things. Okay, I think that covers just about everything. Yeah, pretty much. Is there anything I missed? Yes, there is. So now we're on page 314. So I'm going to look at my real versus imaginary axes again. And so if I have a resistor and an inductor, and the resistor is 10 ohms, and the inductor is also 10 ohms, well, what that means is that my resistor is sitting out here at some vector 10 ohms, and this guy is sitting down there at 10 ohms. And when I add them together, I'm going to have a resistance and a impedance. So this is going to be impedance now. Square root of 10 squared plus 10 squared. Going to be the magnitude, and the angle is going to be 45 degrees. Let's see, 10 squared plus 10, that's 200, right? So that's 10 the square root, 10 the square root of 2, angle 45 ohms. Oh, that didn't work out too well, did it? 10 the square root of 2 ohms, angle 45 degrees. And that would be the impedance of the circuit, and it'd be minus 45 degrees. Okay. Now what is power? Power is I squared R. Okay, so I look at this again, and the circuit's going to have some real power caused by the resistance. Power, real. It's going to have some reactive power. Power, reactive. Am I going the right way? Caused by X of L. It's going to have some apparent power caused by the impedance. Now, when you pay for your power, what do you pay for?
Watts.
Do you pay for the real power, the imaginary power, or the apparent power? Right, so you pay for the apparent power. Okay, so if this guy is 10 watts of real power, and we have 10 watts that is imaginary power, then you're going to pay 10 the square root of 2 watts worth of apparent power. Probably not a good thing. Okay, so what you end up doing in any major manufacturing setting, what's in your plant that's sucking up the most electricity? The lights in the woman's head, the air conditioner for the boss, the 500 horsepower motors. It's normally the motors. The motors are in large part inductive, causing you a big inductive load. This angle between the real power and the apparent power is the power factor. What I want to do is get that angle to be smaller so that my apparent power is closer to my real power. Now, right now we can't do that yet because we need capacitance. But if I put a bank of capacitors in the plant, then I can go and have
That's the big one.
let me see how far I have to go back. I guess I'm okay until then. All right. As I was saying, my x of L is on the imaginary axis in the positive direction. My x of C is my reactance in the other way. So my real guy is there. I've got some apparent power that's there. I got some imaginary power that's there, and I better draw that vector better. That was very professional there, using the big eraser, wasn't it? So what I want to do is I want to bring the apparent power closer to the real power to keep my power bill down. Now, if my power factor were 0.8, okay, that would mean I'm paying 20% more for my electricity than I have to. The money is being sucked up in reactive loads going back between me and the power plant. But if I add a group of capacitors to the plant, this is normally a room someplace about a third of the size of this place, locked with a key that you can't go in because the voltages in there are too high, with a great big high voltage sign sitting on it, then I can bring the power factor closer to zero, and I can save a lot of electricity. So if I'm paying $1 million a month for electricity, which a major plant would do, and I don't control my power factor, I'm throwing away $200,000 a month. That's real money, right? In my house, if I throw away $20 a month on my $40 electric bill, that would be hard to do, right? Yeah, so in my house, I don't have major inductive or capacitive loads. Most of my loads are resistive in nature. It's not an issue for your house, but it is an issue for a manufacturing site. Okay, back to what we're doing. All right, now, I got this inductor. There it is. It's a coil of wire. It has some inductance L, but it also has some resistance R. So the windings of the wire have some resistance. If I have 1,000 feet of 22 gauge wire, it's going to have some resistance associated with it. All right, so the inductor is going to have a quality factor, which is going to be X of L over R sub W. And depending on that quality factor will depend on how it acts in a circuit. Okay, so if I go and I have an inductor, so I got an inductor and my quality factor is 1, and I go and I put a changing AC current on it, then what I see is something that has some peak on like that. I see a voltage to frequency curve looking like that. If I do the same thing and I have a quality factor of 100 associated with it, then and I look at my voltage versus frequency curve, I end up with something that shoots up like that and down like that. High quality. Very, very distinctive in what it looks like. Okay, excellent. On page 318, we see different types of shielded and unshielded inductors. And we already talked about mutual inductance from 2 days ago. That why we have to shield them is because of mutual inductance, not getting in the way. Okay, excellent. Now we'll see what the problem set looks like. As I recall, didn't I already do the easy ones? I think I did. So I did 11. Did I do 15?
We did 15.
I did 15. All right, so now I gotta start with number 20.
Yes.
Now, what are we adding to our vocabulary? We're adding inductive reactance X of L, which is 2 pi FL. 2 pi times the frequency of the circuit times the number of henries the inductor has. Okay, so we're doing that, and then we're also adding transformers, turns primary, turns secondary, voltage primary, voltage secondary, current secondary, current primary, square root of the impedance primary, square root of the impedance secondary. Now, for the math purists in the room, can I have an equation with multiple equal signs? No. Okay, so that means I only use part of these. So I can use those at the same time, calculate something. I can use these at the same time, use those at the same time, use these with these at the same time, but I can't have multiple equal signs. You see the same thing when we write our law of sines. We say sine A over A is equal to sine B over B is equal to sine C over C. But we really don't mean that. We really don't mean that at all. What we mean is that we can take this guy and have him equal to this guy, or we can have this guy and have him equal to that guy, solve them, come up with an answer, and then use it someplace else, but we don't use them all together. That's not a mathematical thing. So this is just a representation of the idea that if I know the primary turns and I know the secondary turns and I know the primary impedance, then I can calculate the fourth thing. So knowing three things, I can calculate the fourth thing, whatever it might be. Okay, so back to number 20. What do we need to do? Find whatever it is that I'm missing. Okay, so is V equal to IR? Yes, it is. Okay, so if I have voltage RMS, and I have current RMS, and I have X of L, then I ought to be able to calculate whatever I'm missing. 180 millivolts, 200 ohms. So the current should be voltage divided by inductive reactance, 90 microamps. Now I think I should probably do that in my calculator, right? 180 minus divided by 200. Nope, 900 microamps. Yeah. So 900 microamps. And the second guy, I know I'm 40 microamps and I'm 18 megohms. That's almost an open. So my voltage is going to be 40 microamps times 18 megohms. And I can just do that in my head. 0, 4 times 8, 3, 2 to carry 7 volts. Is that right? 18 times 40. You're right, 720. How did I get a 3 there anyway? That was really bad. Luckily I have my small eraser, so everything's fine. Otherwise I would have been hosed again. All right, so I've got 2 volts and I've got 100 microamps. Then my X of L will be 2 divided by 100 micro. That's going to be pretty big, isn't it? 2 divided by 100 double E6 minus, boom, 20K. All right, so 23 is next. Questions about that? So that's just a V is equal to IR. Nothing changed. We have to use RMS voltages, RMS currents, because we're dealing with AC. So I couldn't go and say RMS voltage peak and current peak to peak and do a calculation for X of L. I'd have to change the values to RMS before I bothered to do something silly like that. All right, so number 23, calculate the Q. All right, so Q is X of L over R sub W, the resistance of the windings divided by the inductive reactance. And for 50A, okay, so I know the voltage, 12 volts RMS. How do I know that's RMS? Because if it doesn't tell me, it is. If it doesn't tell me it's something else, it is. All right, so and the current is 10 milliamps. I can't buy a peak meter. Oh, I can buy a peak meter, but I don't have one. Right, so if I have a meter, it's going to be, so X of L has to be 12 divided by 10 milliamps. Is that 1.2 K? Okay, so my Q is going to be 1.2 K divided by 8 ohms. 300? 450? 150? 150. Yeah, 150, right. I knew that. Yeah. 1 and 4/8. 1.5. 150. Oh, you want me to slow down?
Yes, please. Oh, yeah.
Oh, well, I have to figure out what the next problem is anyway. 23. All right, 33 is next. Do I have a Q meter in multisim? That's a good question, right? Do I have a measure to? Do I have some way to do that in multisim? Okay, show of hands. How many think I can do it in multisim? How many think I'm blowing steam? Yeah, there. Raimundo's got it right. Vote both ways. That way he can't possibly lose. All right, so I got an inductor. What did we say the inductor was? One point. I forget.
1.2 K?
Oh. 1.2 K. Well, all right. So that won't do me any good. Do I know the frequency? I don't know the frequency. I can't find the X of L. I don't know how many henries I got. I can't do it in multisim. So Raimundo was correct. No matter how I slice this one, I would be hard pressed to do it in multisim because I don't know enough of the parameters to put it in. Okay, working on number 33. You're just plain lucky today. That's all there is to it. 33.
No, you should add this points remaining on the test.
Okay, so here we go.
Brownie points.
Yeah, but when you add something to zero, you just don't get very far. Alright, so we got 80 milliamps going that way. I got a transformer. I got a 12:1 ratio. And I want to know the current secondary. That's what I want to know.
Is that a resistor or
This is a resistor. These are both inductors having to do with, you don't like my picture again?
Oh, I'm just asking. Just to confirm.
Oh my goodness.
It's such a work. Look at that.
You know, it's not a third grade class, you know. Okay, so turns primary to turns secondary equals current secondary to current primary. We remember that from our equations that I wrote down. So 12:1 is equal to current secondary, which I'm looking for, divided by 80 milliamps. Okay, so now we break out our calculator. Current secondary equals 960 milliamps. And then we take our calculator to make sure that's right. 12 times 80. Oh, yes, that's correct. Okay, so that's all there is. There ain't no more there. 39. The peak current in 56A must be limited to 80% of the primary fuse. Determine the minimum value of RL. Okay. So this should be okay. 39, is that what it is? All right. So I got 120 volts, which I probably don't care about, and I've got a fuse. Now who's the idiot that put a 1/4 amp in anyway? And then I got a transformer. Turn ratio is 6:1. Yeah. 6:1. My turn ratio. I got a resistor at this end, and it's variable. And it could be as high as 100 ohms. And we want to find the minimum allowable RL. Okay, so that's what we're going to do. Now, current primary is going to be 1/4 amp times 80%. So that's going to be current primary max allowable. All right, so I take out my calculator. 0.25 times 0.8, 200 milliamps. So 200 milliamps is my maximum current allowed for my problem. Now, current primary divided by current secondary is equal to turns secondary divided by turns primary, implying that 200 milliamps divided by current secondary is equal to 1/6. Okay, so the current secondary max allowed is going to be 6 times 200, 1.2 amps. All right. Now, voltage turns primary to turns secondary equals voltage primary divided by voltage secondary, implying 6 to 1 is equal to 120 divided by voltage secondary. So the voltage secondary is going to be 120 divided by 6, 20 volts. Okay. So my maximum allowed current in the secondary, 1.2 amps. My voltage in the secondary is 20. V is still equal to IR. So resistance minimum, load minimum, is going to be 20 volts divided by 1.2 amps. And at that point, we'd bring out our calculator. 20 divided by 1.2, 16 2/3. 16 2/3 ohms. So that's the minimum allowable resistance to have a 20% safety margin on the fuse blowing. All right. So first thing we did was calculate the maximum allowed current in the primary. Then we calculated the maximum allowed current in the secondary. Then we calculated the voltage in the secondary to get the minimum allowable load resistance. Isn't that great? Now, in general, most of you, when given one step in a problem, can do the problem, right? So if the issue is leave the room, most of you could find the door and get out, right? But if there's two steps in the problem, for example, do 100 push-ups and then leave the room, you probably couldn't do that because there's two steps in the problem, right? Right. Yeah, well, yeah, most of you could at 99 without an issue, I know that. So, and here's a problem that requires 3 steps. Not only does it require 3 steps, but you can't even see the 3 steps because they took too much of the screen. So there, now you can see all 3 steps at the same time. So you draw the picture, you find the primary allowable current, you find the secondary allowable current, you find the secondary voltage, you set V is equal to IR, and find the maximum resistance. 3 steps to work the problem. So that's sort of like 100 sit-ups, followed by 100 push-ups, followed by walking through the door. Oh, wait a minute. 100 sit-ups, 100 push-ups, followed by 2 of your classmates helping you out the door. Something like that, right? Yeah, that'd be good. Yeah, we always did that in the Navy during the PT. We'd do the sit-ups and the push-ups first, and then we'd do the 1.5 mile run. You know, so you'd max out on the sit-ups and the push-ups, and then you'd be puking on the side of the sidewalk. Huh? Is that what happens? Anyway, something like that happens. Okay. What are we doing? How many more problems do I have to do? 1, number 50. Number 50. I would suggest that you just go back and solve all the problems in the book at this point, right? That would be yeah. That way you wouldn't have to watch the football game. You wouldn't have to watch Dancing with the Stars. You wouldn't have to, play with your kids tonight or anything. The circuit shown below has a measured value of 100 milliamps. Assuming the circuit has a value of K equals 0, determine the value of L2. Okay, so K is equal to 0. What does that mean?
Easy.
That means no mutual inductance. So these guys are shielded. They're not going to interfere with each other. Okay, so now I got this thing that's 2 volts. Can I put this in multisim and make it work? No, because I don't know the frequency. Multisim would not like an AC circuit without a frequency. 470 microhenry, 9 volts. Now, is that possible? Is it possible to have 2 volts on the source and 9 volts across one of the inductors? Is that possible? Well, yes, it is. Now, how is that possible? Remember the Q, the quality factor we're talking about? So you have some winding resistance that the real voltage is dropping across, but there's imaginary voltages across those guys. Those imaginary voltages aren't limited by this 2 volts. In fact, why don't I don't know. Why don't I do something weird? Oh, no problem, right? All right, so I'm going to do that, and I'm going to go get a voltage thingy. Yeah, that was a good sources. No, yeah, AC. There we go. I got some AC thing. And then we're going to put a voltmeter. Is this a voltmeter? All right, there's a voltmeter. So I'm going to put a voltmeter there, and I'm going to put a voltmeter here. And the only thing else I need is a lousy resistor, right? I need a ground. Okay, so I run that guy there, run this guy over here, that guy down there, ground over here. Boom, 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 boom. Okay, that's what I'm going to do. Turn it on. So I've got 120 volts RMS here. What are those voltmeters saying? Well, I can stop that. There, I stopped it. Now are you happy?
90K.
90,000.
Holy moly.
Well, that's not too bad.
It'll zap you.
No, the idiot instructor put an amp meter in the volt instead of a voltmeter.
What a guy.
I mean, talk about stupidity. Guys weren't even paying. I almost got away with it too, didn't I? Almost did. But what does Kirchhoff's law say? It says the voltage that you go up has to be the voltage as you go down, right?
Yes.
All right, just wondered. So I've got 120 volts. I go up, and I go down microvolts and up millivolts. What the heck? All right.
Yeah.
Right here is a Bode plotter. Okay, so we're going to go here to here, and then we're going to go there to there. Here, we're going to do that, and then we're going to turn it on. We need a resistor.
Waco.
Yeah, Waco, Texas. Is that what we're talking about? So we'll grab a resistor. Come on, where'd my resistor go? All right, so I got a resistor. Now I'm better. Thank you very much. They're giving me 2. All right, now I got a resistor. That's better. I'm going to put this guy over here. All right. Oh, that is definitely the pits. What am I doing wrong? Okay, I went across that guy, and I'm across these guys. That's my output. Why am I not seeing anything?
Why the resistor makes a difference if it's at the end of the circuit? With the ground, close to the ground.
Well, I'm just current limiting, that's all. All right, so I'm flatlined for some reason. Why am I flatlined? Oh, this guy's so small. We'll make him. Yeah, that's probably better. Still pretty much flat. I don't know what I'm doing wrong. Doing something wrong. Okay, well, we'll just go back to the problem and not worry about that. All right, so there's no mutual reactance. I've got this, I got that. This is 9 volts. That's 2 volts. Isn't that nice? So the issue is, determine L2. All right, so current RMS is equal to 100 milliamps. So X of L has to equal voltage RMS divided by current RMS. 2 divided by 0.1, this is 20 ohms. Okay, so, and that'd be X, so X sub L total is 20 ohms. What's the problem?
XL equals what?
I'm just finding X of L total.
Right.
I know the RMS voltage,
Yes.
I know the RMS current, I
Oh,
know
okay, iron.
X of L. All right, now, X of L total is also equal to what? It's equal to 2 pi F L1 plus 2 pi F L2, right? And I know 2 pi F L1. So 20 is equal to 470. No, that's L1. It's equal to 2 pi F 470 microhenry plus 2 pi F L2. Okay. I know that. What else do I know? I know X sub L2. X of L2 is going to be 9 volts divided by 0.1 amp. It's going to be 90 ohms. $90. Just like this was 20, that was 90. If it's 90 ohms, Yeah, I don't see how this is gonna work out. X of L. Okay. Okay. 20 has to equal 2 pi f 470 millihenry plus 90 ohms. Okay, I got that. I can calculate F. F is equal to 20 minus 90 divided by 2 pi 470 microhenry. Okay, so my F is going to be negative frequency. I love it. I love negative frequency. Times 2 times pi 70 with a minus sign divided by 2 divided by pi divided by 470 double E 6 minus 15.9 15.1 kilohertz.
15.1?
Yeah, 15.1 kilohertz. Okay, now, that being the case, X of L2 has to be 2 pi FL2. 90 has to equal 20 minus 15.1 K times X of L, X sub 2, L sub 2. So L sub 2 is going to be, okay, I've got this number already, 1 over times 90 divided by 2 divided by pi equals, change to engineering notation, 900 minus 950 microhenry. Okay. All right, so we're in multi-sim, and we'll get rid of this guy, and we'll get rid of, why can't I get rid of him? We'll get rid of this guy, we'll get rid of this guy, we'll get rid of this guy, and we'll get rid of that guy. And we'll put in another inductor. Right there. And we'll get rid of this guy. And we're going to hook up him to there. And him to here. And we're going to go 2 volts. 2 volts. And the frequency we want is minus 15 K. Okay. Okay, minus 15K. And we want this guy to be 470. 470. I guess I'm going to have to get it one. 470.
That's what you're looking at. Okay.
470. Milli went too far. 6. There it is. 470 micro. Okay. And the other guy was supposed to be what?
That one, according to you, 90?
900,
950.
950. $950. Oh, that's the wrong one.
Keep going.
All right, that's as close as we're going to get. And we want it to be negative. Want it to be negative. And then we want to put a voltmeter right here. Is that a voltmeter? Yes, it is. About time I get a voltmeter. And this time, oh, you know what was the problem before? I had DC voltmeters in an AC
You
circuit.
might have mentioned that.
Is it-
Alex, you don't count.
Huh? Alex, did you mention that?
Yes, it did, but you don't count.
Well, you didn't say it loud enough. All right, so we need an AC voltmeter. All right, I'll turn this guy on.
That was good.
All right, so it doesn't like something. Let's see.
Spies. Holy moly.
Yeah, so it doesn't like something. All right, so we're going to change this guy to positive and see if that helps any. I don't think it's going to like the negative frequency. You know what I mean?
That's what it was.
Ooh, look at that. Not bad. Negative frequency. Almost. Is that not almost 6?
What?
Huh? What is it, 2 point, isn't 2.3 almost 6?
No.
No.
What do you mean no?
Relatively.
Yeah, I mean,
In the grand scheme of
in the
things.
grand thing of things, that's pretty darn close to 6.
Well, if I'm coming with the answer and I think it's right,
Yeah.
yes, but you will say
So-
yes, no.
My feeling is that number 50 is not something that can be solved. That 2 inductors like that,
That's your homework.
you cannot have 9 volts if you only have 2 over there. So that's my
So the
opinion.
answer should say no, impossible.
Well, I don't think we have answers in the back, do we? And if we do,
We're
then,
not even.
It should be.
yeah. So there's no answer to 50. But I
Google
think
it.
that's no, we're not going to Google it. What if I change this to plus 15K? What would happen then? See, it doesn't care if it's plus 15 or minus 15. It's going to give you the same answer. And it's not going to let me have a negative Henry thing. Okay, see you next week.
Grazie.
We're done with chapter 10.
Was it regular? You failed to tell me that we were coming to this class. I was still waiting over there for you to give me an answer for the things I was doing. Then I realized I looked at my watch and I was like, yeah, it's time to go.